In this video, we are going to give some reference to the more examples of lock-free data structures. So far we studied queue, stack, and linked list, and they are the most basic ones. And to study the lock-free concurrency, you probably need to start with those data structures. But there are many other interesting data structures. So please refer to many data structures like this. For example, there is a circular buffer, or what is usually called ring buffer. So this buffer has a fixed size array, and there are two ends of the queue. So in the first end, we are going to push value, and the other end, we are going to pop a value from that. So this, you can think of this as a fixed length, fixed sized queue, array queue. And what is particularly interesting about this is that you are going to reuse the queue as a circle. If you use up the buffer by pushing all the values, and then you're going to go to the first element. And if it is empty, then you're going to push a value to that. So basically the buffer array is used as a ring. The next element of the last item is the first item. So that's the reason why it is a circular buffer or a ring buffer. And concurrent ring buffers are very widely used among communications between, for example, CPU and the accelerators, CPU, GPU, CPU, FPGA, or even the communication among the accelerators. So this is probably and also this is used used for communication between the user space and the kernel space in the operating systems. For example, if a user program wants to send data to the kernel asynchronously, it just adds the item to the queue. And the queue is a circular buffer. So that's basically what's going on in how it can be used in many use cases of asynchronous communication among multiple agents. Also, there are data structure that is called chase lab worker stealing that queue. And that queue means that it is a queue, but you can push and pop at the both end of the queue. But worker stealing that queue is a little bit different. So a single thread can push and pop from a single end, and for the other end, multiple threads are able to pop data from the other end. So it is basically a stack, but another thread, one thread is using it as a stack, but the other threads may steal an item from the other end. The oldest item may be stolen by the other threads. So that is the basically stack with a stealing end. And it is widely used in task management, as I will explain in the next slide. So its design is described in Manual, and in this article, I specifically proved the correctness of this worker stealing the queue. So if you're interested in this, please read the papers and my proof about this worker stealing the queue. And there are also hash tables, binary trees, and registries, and many other concurrent data structures that is lock-free. Among them, the hash table is basically the homework 5. For homework 5, you are going to implement the split ordered linked list, which is basically a concurrent hash table, concurrent resizable hash table. And in the previous semester, the homework 2 was about binary search tree that is concurrent, but in this semester we didn't do that. Also, there are concurrent registry, concurrent B tree, concurrent transactional tree, concurrent copy and write the data structures, etc., etc. There are so many concurrent algorithms, and they all share a similar spirit that they want to allow more concurrent accesses to the different part of the data structure. So that is basically the goal of all these data structures. And if you're interested, please go search for these data structures and see what's going on there. And among them, today we are going to study a little bit about work stealing a little bit more. As I said, work stealing is a stack basically, and only one thread can push and pop an item to the stack. Recall that stack is a LIFO, last in first out. So the newest item is popped by the owner of the stack. But what is interesting about this worker stealing deck queue is that the other end, the oldest item, it can be stolen by the other threads. So why this is important, why this notion is important is that you can dynamically distribute the many work across multiple threads very efficiently using this work stealing deck queue. For example, there are 8 threads. So this figure illustrates 8 threads, and each thread has a list of work. For example, this thread has 2 works, and it is working on some work, and this is working on some work, but there's no remaining work. It has many work. It has 1 work, and this is working on 1 work. But the problem is that, in this and this thread and this thread, they don't have a remaining work. Then what do we do? What we do is that we want to steal work from the other threads. And suppose that this thread, the middle thread, it has many work. And if the other threads acknowledge that, they want to steal the work from this thread. That is basically picturing that there are a lot of work that is stacking up here, and this thread and this thread are stealing some of the work from the middle thread. So by doing so, we can efficiently and dynamically distribute multiple work across multiple CPUs or cores. And it will achieve a very good performance, even much better than static scheduling, because it is guaranteed that no thread is just idle. If there is some work to do, then it is automatically distributed among multiple CPUs. As a result, the throughput or utilization may be increased. But in order for this scheme to work fast, we have to make sure a few properties to hold. The first thing is that we need to divide this work a little bit. As much as possible. Not as much as possible, but we at least needs to have many work so that they can evenly distribute to multiple threads. Suppose that there is only 1 work that is very, very super big. Then even though we apply this scheme, the only 1 thread can work on the big job, and its utilization will be bad. Only if the big job can be split and distributed across multiple cores, the throughput will be increased. That's the reason why we need to guarantee that we adequately split the job. But if we split the jobs in a too fine-grained way, it is the case that the synchronization among multiple CPUs, each cost will dominate the processing time. So we need to somehow adequately distribute the work. If the work is, for example, too fine-grained and there are too many tasks, task management cost will be going higher and higher. So we want to prevent such a case. So it doesn't need to. It should be. It should not be too big, and at the same time, it should not be too small. And furthermore, we need to guarantee that the thread that is owning the queue, the thread should be fastly accessing the queue. So the work stealing, the stealing event happens very rarely. It happens only if there is a thread that has no more work to do. But usually it is a very rare event compared to the event that a thread is pushing or popping an item to its job queue. So we need an asymmetry here. If one thread is accessing its own queue, it must be fast. If the other threads are stealing the queue from the queue, then it can be a little bit slow. So there's an asymmetry. And KAIST is trying to exploit this asymmetry by designing the algorithm in such a way that push and pop is very fast, but stealing is a little bit slow. So it is implemented in that way. Again, if you're interested, please go read the implementation and the paper about work stealing the queue. Okay, this is pretty much everything of I prepared for this video. There are many other examples of lock-free data structures, and the work stealing queue is one of the most interesting example among the multiple lock-free implementations. So if you're interested, please go study the blog post or the papers, etc.